Welcome back to our video module on quantum mechanics. In our previous video, we used a time-independent Schrodinger equation to identify a wave function in the infinite square well. We found that the wave function was something of the form of sine of x. However, if we're going to look at this more carefully and play with this more, we need something than just a basic form. One could reasonably ask, what is the actual equation for the wave function? Today, we're going to be taking a more in-depth look at solutions to the wave equations for the infinite square well potential. In addition, we're going to look at characteristics of the Schrodinger equation to understand how to apply it in these scenarios. Now, what I'd like to do is start off again with our time-independent Schrodinger's equation. And remember that this term is going to go to zero in the region between 0 and a. This is what gave us an equation of the form negative h bar squared over 2m d squared dc dx squared equals EC, and we knew that that is going to be some sort of sinusoidal form. Now, fortunately, the actual solution to this equation is pretty easy to identify. Now, fortunately, identifying the solution to this wave equation is going to be pretty simple, simply because we know how to contract and expand periodic functions. In this case, the solution is sine of pi x over a, and I'm saying it's roughly equivalent because we haven't done our vertical scaling yet. And now might be a good time to remember how we got this. First, we knew that the form was going to be of some sinusoidal function. Secondly, we knew that the wave function was zero wherever the potential is infinity. And we know that the wave function is continuous, so it's going to go to zero at 0 and 0 at a. And in fact, what we've identified is the first solution. There are more. Why don't you put the video on hold for a minute and see if you can come up with one further solution that satisfies this criteria. Welcome back. Hopefully you came up with something that follows some of these same rules that I'm writing down here. First, we have a wave function that goes to 0 outside of 0 to a. Secondly, it's going to follow some sort of sinusoidal path, but we didn't say how many nodes there were or how much it's compressed, which means we could just as easily have this right here. We'll call this solution C2. And we know enough about trigonometry that we can just write down the basic form of the equation, sine of 2 pi x over a. Finally, I've drawn out the third solution to the Schrodinger's equation in the infinite square well. And in fact, if we look at these three solutions right here, we can start to see some sort of theme emerging. If we think of n as the number of half wavelengths, our first solution had 1, second solution had 1, 2, third solution had 1, 2, 3. We can write down a form of the wave function as sine of n pi x over a. And because we haven't scaled these vertically yet, we're noting that this is the form of the equation and not the exact solution to the equation. Note as well that if we were to draw a line straight through the center and think of this as our origin or the center of where we're looking, that we see these functions oscillating between even and odd. And one can imagine if we were to do C4, C5, C6, that this oscillation would continue between even, odd, even, odd. This type of behavior will become even more interesting later on. So in summary, we've been able to do more than just sine x. We've been able to see how much sine has been shrunken or stretched by using pi over a for each half wavelength. And we've seen that there's in this case, infinite number of solutions based on how many half wavelengths are in the solution, or a better way that we'll talk about it further is how many nodes in each solution. This has given us a general form of solutions in the infinite square well of sine n pi x over a. Join us next time as we learn how to scale it vertically so that we get an actual solution.